Welcome back to the Deep Dive, where we get straight to the knowledge that matters most to you. Today, we're diving into something really special. It's a rapid-fire knowledge audit for anyone looking to conquer the NVIDIA Certified Associate. Multimodal Generative AI Cert, that's the NCA-GENM.
Right.
Think of this as your personal audio quiz. We've crafted it not just to test you, but, to give you a focused revision of those critical domains.
Exactly.
Our mission: help you pinpoint your strengths, maybe uncover some aha moments, and really master the concepts. Okay, let's unpack this.
Yeah, absolutely. And this isn't just about ticking boxes or finding the right multiple choice answer. It's really about understanding the core concepts behind multimodal generative AI. We've pulled questions from, well, all the key areas.
Which are?
We're talking core machine learning, data analysis, experimentation, the multimodal data itself, performance optimization, and even software development aspects. It's a targeted revision, and like you said, invaluable for success. We want you to get the comprehensive picture, not just memorize facts.
Understanding the why, not just the what.
Precisely. The why is often much more important in the long run.
Totally agree. So whether you're taking mental notes or actually scribbling them down, get ready. We're about to jump into our quiz. I'll lay out the question and the options, give you a moment to think.
And then I'll jump in with the correct answer and hopefully some useful explanation and insights.
Perfect. Ready. Let's kick things off with Domain 1, Core Machine Learning and AI Knowledge. Okay, question 1. Which NVIDIA technology is best for efficiently training large-scale multimodal AI models using distributed computing? Is it A, NVIDIA CUDA, B, NVIDIA NCCL, C, NVIDIA QDNN, or D, NVIDIA Digits? Take a moment.
All right, the correct answer here is B, NVIDIA NCCL.
NCCL.
Yeah, NCCL. Stands for NVIDIA Collective Communications Library. It's specifically designed for handling the communication efficiently across lots of GPUs, even across multiple machines. When you're dealing with these huge multimodal models, you need that kind of coordination between all the processing units.
So it's different from just CUA.
Right. CUDA is more the general platform for programming GPUs. CUDNN provides primitives specifically for deep learning operations. And Digits was more of a web app for training. NCCL is really about the communication side of distributed training. Think of it as the backbone for scaling those massive, complex models. It's what lets all the GPUs work together effectively on one giant task.
The backbone, like an orchestrator.
Exactly, an invisible orchestrator. Without something like NCCL, training models like, say, GPT-4 across hundreds or thousands of GPUs just wouldn't be practical.
Got it. That really clarifies its specific role. Okay, question 2. What's the primary role of neural networks in multimodal AI systems? Options: A, perform linear regression; B, integrate and learn from multiple data types simultaneously; C, execute SQL queries; or D, provide data encryption.
Okay, this one should be fairly clear. The answer is B.
Integrating and learning from multiple data types.
Yes, that's the core strength of neural networks in this context. They can take diverse inputs, images, text, audio, you name it, and learn meaningful patterns and relationships between them. This leads to more comprehensive understanding and prediction than using just one data type alone.
And the other options are just not it.
Right. Linear regression is basic stats, SQL is for databases, encryption is security. We're not the main job of the neural network here. What's interesting is how they integrate. They don't just mix the data, they often learn a shared, richer representation that captures insights from all modalities.
A unified representation. Okay, that's a key idea.
Definitely. It's about finding those deep connections.
Excellent. Question 3, still in core ML and AI. Which algorithm is most effective for training a neural network that processes both audio and visual data simultaneously? A, K-means clustering; B, convolutional neural networks, CNNs; C, recurrent neural networks, RNNs; or D, multimodal transformers?
This gets into more specific architectures. The best answer here is D, multimodal transformer.
Transformers again, they seem to be everywhere.
They really are. And for multimodal tasks, they're particularly powerful. They use attention mechanisms to weigh the importance of different parts of the input, both within and across modalities. So they can learn how sounds relate to visuals, for instance, in a very sophisticated way.
And why not CNNs or RNNs?
Well, CNNs are great for spatial data like images, processing pixels close together. RNNs are designed for sequences like text or time series data. While you can combine them in various ways, multimodal transformers are specifically architected to handle and integrate multiple modalities right from the start, using that attention mechanism. K-means is just for clustering data points.
So the attention mechanism is the real game changer for fusing different senses in AI.
You could say that. It allows the model to dynamically figure out what's important across the different data streams. It's a big step towards a more holistic understanding.
Fascinating stuff. Okay, let's shift gears. Domain 2, data analysis. Question 4. You're doing data analysis for a multimodal AI project with video and audio. What's a crucial initial step for data quality? Is it A, randomly selecting a subset, B, normalizing the data, C, checking for synchronization between audio and video, or D, applying data augmentation?
Okay, initial step. Crucial. The answer is C. Checking for synchronization.
Synchronization first, before anything else.
Absolutely. For temporal data like audio and video, if they aren't perfectly aligned in time, your model is learning garbage. Imagine training a lip reading model where the audio is half a second off.
Yeah, that wouldn't work at all.
Exactly. So ensuring that the sound matches the action frame by frame is fundamental. Things like normalization, subset selection, augmentation, those are important too, but they usually come after you've got properly synced data.
So what does this all mean for real-world applications?
Well, think about understanding a conversation in a video. If the sound doesn't match the lip movements or the timing of events, any analysis like figuring out who said what or the sentiment expressed just falls apart. Synchronization is paramount for integrity.
Got it. Foundational. Okay, question 5, still data analysis. In a system processing text and images, which visualization technique helps identify how different modalities contribute to a decision? A, confusion matrix, B, attention maps, C, ROC curve, or D, histogram?
The key here is visualizing contribution. That points to B, attention maps.
Attention maps. We mentioned attention mechanisms earlier.
Exactly. Attention maps visually show you which parts of the input, which words in the text, which regions in the image the model paid the most attention to when making its prediction. This gives you insight into how it's using each modality.
And the others. Confusion matrix, ROC, histogram.
Confusion matrices evaluate classification accuracy. How many times was A predicted as B? ROC curves help assess binary classifiers across different thresholds. Histograms just show data distribution. None of them specifically visualize the model's focus across modalities like attention maps do.
This raises an important question about transparency, right? Like seeing inside the AI's thought process.
Precisely. Attention maps are a key tool for explainable AI, or XAI. They help us understand why the model made a certain decision by showing what input features it found most salient. It helps build trust and allows for better debugging.
Really valuable. Okay, excellent. Let's move into experimentation. Question 6. You're doing prompt engineering for a multimodal chatbot, maybe using NVIDIA Jarvis. Riva now, I suppose.
Yes, the framework evolved into Riva.
Right, Riva. You experiment with prompt styles. What indicates a successful prompt engineering process? A, faster responses. B, more engaging and contextually relevant responses. C, less computational resource use. Or D, shorter responses on average.
Success in prompt engineering specifically. That would be B. The chatbot generates more engaging and contextually relevant responses.
So it's about the quality of the output.
Exactly. Prompt engineering is about crafting the input to guide the AI towards generating the desired kind of output, one that's accurate, relevant, coherent, and fits the context. Faster responses or low resource use are efficiency metrics, important, but not the direct goal of refining the prompt itself. Shorter responses aren't necessarily better either.
What's fascinating here is how it feels less like programming and more like guiding.
That's a good way to put it. You're not writing explicit code. You're shaping the AI's behavior through carefully crafted natural language instructions or examples. It's about guiding its creativity and knowledge to get meaningful interactions.
Guiding creativity. Cool. Okay. Question 7, still experimentation. When evaluating a multimodal model's performance using something like NVIDIA Triton Inference Server for a real-time application, which metric is most important? A, training time, B, inference latency, C, model size, or D, number of parameters?
For real-time applications, the keyword is real-time. So the answer is B, inference latency.
Latency. The delay, basically.
Yes, the time it takes from getting the input to producing the output. In real-time scenarios, think self-driving cars reacting to obstacles or live video analysis, that response time has to be incredibly fast. High latency makes a model useless for these applications, no matter how accurate it is on paper.
So training time, model size, parameters, they matter, but not for the immediate real-time performance.
They matter for development, deployment constraints, cost, etc. But when the application is running live, latency is often the critical bottleneck. If we connect this to the bigger picture, a model could be 99.9% accurate, but if it takes 2 seconds to identify a pedestrian stepping into the road,
it's too late.
Precisely. In many real-time cases, latency is king.
Makes perfect sense. All right, let's transition to domain 4, multimodal data. Question 8. You're annotating a multimodal dataset using NVIDIA's TAO toolkit. What's the most important consideration? A, ensuring annotations are in JSON format. B, aligning annotations across modalities for temporal spatial consistency. C, using only pre-trained models for annotation. Or D, annotating only the most frequent modality.
We touched on this earlier with synchronization, and it's key here too. The answer is B, aligning annotations across modalities.
Consistency again.
Yes. Whether it's time alignment for video audio or spatial alignment for image regions and text descriptions, that consistency is critical. The model learns associations based on these aligned annotations. If they're off, the learning is flawed. JSON is a common format, but the format isn't as fundamental as the accuracy of the alignment. Pre-trained models can assist annotation, but alignment still needs verification, and only annotating one modality defeats the purpose of multimodal learning.
Here's where it gets really interesting. That analogy you used before about teaching a child.
Right? Teaching reading and object recognition. If the words you point to don't match the object the child sees at that moment, they won't connect apple, the word, with the image of an apple effectively. Same principle applies here. Accurate, aligned annotations are crucial for the AI to learn the connections.
That really drives it home. Okay, question 9. In processing multimodal datasets, why is including diverse data sources important? A, to increase data set size regardless of quality. B, to ensure the model generalizes to different real-world scenarios. C, to focus learning on one data type. Or D, to simplify preprocessing.
The key benefit of diversity is B, ensuring the model can generalize.
Generalize, meaning it works well outside the training data.
Exactly. The real world is incredibly varied. If you only train your model on, say, perfectly lit studio images and clear audio recordings, it will likely fail when faced with blurry phone pictures, noisy environments, different accents, etc. Diverse data covering various conditions, sources, demographics makes the model more robust and reliable when deployed.
So it's not just about getting more data, but the right kind of varied data.
Absolutely. Quality and diversity over sheer quantity. Focusing on one data type is the opposite of multimodal. And diverse data often makes preprocessing more complex, not simpler, but it's worth the effort for robustness.
So what does this all mean for practical application, like your traveler analogy?
Right. A model trained on diverse data is like a well-traveled person, more adaptable, less likely to be surprised or confused by novelty, better equipped to handle the unexpected variations of the real world. A model trained narrowly is like someone who's never left their village.
Powerful comparison. Okay, final question in this domain. Question 10. A critical consideration when processing audio data for a multimodal system that also includes visuals. A, ensure MP3 format. B, align audio temporally with visual data. C, convert audio to text first. D, prioritize audio quality over synchrony.
We've hit this theme hard, haven't we? It's B again. Aligning the audio data temporally with the visual data.
Synchronization seems to be a recurring critical point for multimodal.
It absolutely is, especially when time is involved. You need the sounds to match the sights precisely for the model to understand the event correctly. MP3 is just one format. Converting audio to text throws away valuable information like tone, emotion, background sounds. And prioritizing quality over synchrony is misguided. Perfectly clear audio that's out of sync is less useful than slightly less clear audio that's perfectly timed.
This raises an important question. If they're not aligned, how can the AI understand the event? Like that dubbed movie example.
Exactly. Watching a badly dubbed movie is confusing and disrupts understanding. Same for the AI. That temporal link between seeing and hearing is fundamental for coherent interpretation.
Got it loud and clear. Synchronized, I hope. Let's move to performance optimization. Question 11. Which NVIDIA technology helps optimize performance by reducing latency during inference? A, NVIDIA Tensor. B, NVIDIA Kudu Toolkit. C, NVIDIA Nsight Systems. Or D, NVIDIA Jetson Nano.
For inference optimization, especially latency reduction, the answer is A, NVIDIA Tensor.
Tensor, what does it actually do?
Think of it as a compiler and runtime specifically for trained deep learning models.
Yeah.
It takes a model you've already trained and applies various optimizations like fusing layers together, choosing efficient kernels, and often converting the model to use lower precision arithmetic like FP16 or INT8, all to make it run much faster and with lower latency on NVIDIA GPUs.
So it's a post-training step.
Correct. CUA Toolkit is the broader development environment. Nsight Systems is for profiling and debugging performance bottlenecks. Jetson Nano is a small hardware platform for edge AI. TensorTie is specifically about optimizing the deployed model for speed.
What's fascinating here is that it's like a specialized tuner for the AI engine.
That's a great analogy. It tunes the model for peak performance at deployment, ensuring it responds super quickly, which is critical for many applications.
Right. Okay, question 12, still performance optimization. In energy-efficient design for multimodal AI, which strategy is most effective? A, increasing batch size indefinitely, B, using mixed precision training, C, adding more layers, or D, switching to a CPU.
For energy efficiency on NVIDIA hardware, the most effective strategy listed is B, using mixed precision training.
Mixed precision, using different levels of numerical precision.
Exactly. Combining lower precision formats like 16-bit floating point FP16 with the standard 32-bit FP32. FP16 calculations require less memory and less computational power, and NVIDIA GPUs have specialized tensor cores that accelerate these operations dramatically. This leads to faster training and inference and significantly lower energy consumption, often with little to no loss in accuracy.
And the other options are less efficient.
Yes. Increasing batch size helps throughput up to a point, but hits limits and doesn't inherently cut energy per calculation. Adding layers makes the model less efficient. And CPUs are generally much less power efficient for parallel deep learning workloads compared to GPUs.
If we connect this to the bigger picture, energy efficiency is becoming a major concern, right?
Huge. As models get larger, their energy footprint grows. Techniques like mixed precision are vital for sustainable AI development, reducing both operational costs and environmental impact. It's a key tool in the responsible AI toolkit.
Very important point. Okay, we're on to our final domain, software development. Question 13. Which Python library is essential for a multimodal AI app needing real-time video processing on NVIDIA hardware? A, OpenCV, B, NumPy, C, Matplotlib, or D, Pandas?
For real-time video processing, the standard choice is A, OpenCV.
OpenCV, why that one?
OpenCV, or Open Source Computer Vision Library, is packed with functions for image and video analysis, manipulation, and real-time capture. Crucially, it has excellent integration with CADA, allowing many of its functions to be hardware accelerated on NVIDIA GPUs. NumPy is for numerical arrays, Matplotlib for plotting, Pandas for data structures and analysis. They're all essential in the Python data science stack. But OpenCV is a specialist for computer vision and video.
Here's where it gets really interesting. It's the bridge between the raw video stream and the AI model.
In many ways, yes. You use it to grab frames, maybe do some pre-processing like resizing or color conversion, potentially run some classic CV algorithms, and then feed the data into your neural network. Its GPU acceleration is key for real-time performance.
Makes sense. Question 14. What practice is crucial for efficient system integration when deploying a complex multimodal AI model with NVIDIA tech? A, single-threaded processing, B, microservices architecture, C, storing data in local SQUIAT, D, developing entirely in Java.
For complex systems, the best practice here is B, implementing a microservices architecture.
Microservices, breaking the system down.
Exactly. Instead of one giant monolithic application, you break the system into smaller independent services that communicate with each other, often over a network. For example, you might have separate services for video ingestion, audio processing, text analysis, the core multimodal model inference, and the final output generation. This makes the system much more scalable, maintainable, and resilient. Different teams can work on different services, and you can scale individual components based on load.
And why not the others?
Single-threaded is a performance killer for this kind of work. SQUIAT is a lightweight local database not suitable for large-scale distributed data. Java is a capable language, but the AML ecosystem, especially around NVIDIA tools, is predominantly Python-centric, making integration easier there.
So what does this all mean for development teams? It sounds like a more manageable way to tackle huge AI projects.
It absolutely is. Microservices allow you to manage complexity by breaking it down. It promotes modularity and independent deployment, which is a game changer for building and evolving large-scale, multimodal AI systems.
Got it. Last question. Question 15. Which NVIDIA technology integrates real-time voice recognition into a multimodal AI system in Python? A, NVIDIA CUDA, B, NVIDIA Riva, C, NVIDIA Omniverse, or D, NVIDIA Clara?
For real-time speech AI, the answer is B, NVIDIA Riva.
Riva again. We mentioned it with the chatbot prompt.
Right. Riva is NVIDIA's SDK, specifically for building and deploying conversational AI applications. It provides pre-trained models and optimized pipelines for tasks like automatic speech recognition, ASR, text-to-speech TTS, and natural language understanding, NLU. It's designed for high performance and real-time responsiveness, making it ideal for integrating voice interfaces into multimodal systems.
And it's distinct from the others.
Yes. CUA is the underlying platform. Omniverse is for 3D simulation and collaboration. Clara is focused on healthcare AI. Riva is squarely aimed at speech and conversational AI.
This raises an important question. How do you get truly conversational AI? Riva seems like a key enabler.
It is. It provides those optimized building blocks, the high-accuracy speech recognition, the natural-sounding voice synthesis that are essential for creating smooth, interactive experiences. It bridges that gap between raw audio and intelligent interaction, all in real time.
Fantastic. Wow, okay, we really covered a lot of ground today. From core ML fundamentals, data analysis nuances like synchronization, experimentation, including prompt engineering, and latency.
Multimodal data handling, with alignment and diversity, performance optimization using TensorArt, and mixed precision.
And essential software development practices like OpenCV and microservices, plus tools like Riva. You've just had a pretty intense, condensed tour through the key concepts for the NCA-GENM. How did you do listening along? Did you have some aha moments, maybe spot some areas to brush up on?
Yeah, it really highlights how interconnected all these pieces are. You can't really isolate one domain. They all influence each other in building effective multimodal AI systems. And, if you listened through that and thought, I need more practice, or I want to solidify those weaker areas, there are tools designed specifically for that. We should mention FlashGenius.
Right, FlashGenius. Tell us about it.
It's a comprehensive prep tool for the NCA-GENM cert. It offers things like unlimited practice questions covering all these domains we discussed. You get full-length exam simulations that feel like the real thing with scoring. It also uses AI itself to track your performance and pinpoint where you need more focus.
Personalized study plans.
Exactly. Adaptive learning, personalized plans, plus interactive flashcards, insights from common mistakes other learners made, multilingual support, even a Pomodoro timer for focus. It aims to be that one-stop resource hub, with study guides and cheat sheets, too.
So it's more than just a question bank.
Much more. This raises an important question. Why struggle piecing together resources when you can have an AI-guided path? One that adapts to you, helps you understand the why, not just the what, and builds confidence systematically.
So if you're serious about accelerating your NCA-GENM prep, definitely check out FlashGenius. It sounds like a smarter way to prepare, potentially saving time and boosting confidence. And as you continue your journey in multimodal generative AI, maybe take a moment to consider this. How can leveraging smart adaptive tools like these not only help you pass an exam, but truly empower you to build, optimize, and innovate with the complex intelligent systems that are shaping our future? Something to think about. Thanks for joining us on the Deep Dive.